They didn't drop the bomb from the sky. They buried it, nearly 2 kilometers beneath solid rock. And then, they detonated it. In November 1971, on a remote island in Alaska, the United States carried out the largest underground nuclear test in its history. The location was Amchitka Island. Isolated, wind-scoured, thousands of kilometers from major cities. On paper, it was the perfect place. No civilians. No towns nearby. Only rock, ocean, and seismic instruments. The goal was not destruction. At least, not on the surface. By the late Cold War, nuclear testing had moved underground. Atmospheric explosions had proven too dangerous. Radioactive fallout could not be contained. So the strategy changed. If the bomb could be buried deep enough, the explosion could be trapped, measured, controlled. That was the theory. Amchitka had already been used before. In 1965, a test called Long Shot. In 1969, another called Milrow. Each time, the device was placed deeper. Each time, the yield was increased. And each time, officials concluded the same thing. The ground held. So the next decision followed naturally. Go deeper. Go stronger. Push the limits of containment. The test was called Canakin. The device was lowered nearly 1.800 meters underground. The explosive yield was estimated at 5 megatons. Far more powerful than Hiroshima. Buried beneath an island that sat on an active tectonic zone. Engineers believed the depth was sufficient. Geologists believed the rock would absorb the shock. Models predicted the damage would remain sealed below ground. The surface, they said, would barely notice. This was not an accident. It was a calculated decision. A belief that human engineering had finally learned how to detonate a nuclear weapon without breaking the world above it. But what mattered was not what they intended to test. What mattered was what they had asked the ground to endure. And whether the earth would agree. The decision didn't come all at once. It came step by step. Each test was meant to answer a question. And each answer only led to another experiment. In 1965, the first device was lowered beneath Amchitka, about 700 meters down. The test was called Long Shot. Its purpose was not the weapon itself, but the signal it produced. Scientists wanted to understand how a nuclear explosion looked when it traveled through solid rock. The ground absorbed the blast. There was no visible disaster on the surface. So they went further. 4 years later, another device was prepared. This time, it was placed deeper, over a kilometer beneath the island. The test was called Milrow. Its yield was far larger, nearly a megaton. Again, the island remained standing. Again, the damage appeared contained. From the outside, the conclusion seemed obvious. Depth worked. Rock worked. Containment worked. And with each successful test, confidence grew. Models became more ambitious. Predictions became more optimistic. If 1 megaton could be buried safely, why not 5? By the early 1970s, underground testing was no longer about whether it could be done. It was about how far it could be pushed. Canakin was designed to be the final proof. The device was enormous. The yield unprecedented for an underground test. Engineers calculated the depth carefully. Nearly 1.8 kilometers below the surface. According to simulations, the explosion would collapse inward, crushing the cavity, locking the damage below layers of solid rock. From above, the island would barely register the event. That was the expectation. What mattered now was not caution, but precision. Not whether the ground might react, but whether it could be predicted. The test site sat on an active tectonic zone, but it had held before. And so the reasoning followed a familiar path. It worked last time. It should work again. What had once been an experiment had become a calculation, a belief that the Earth itself could be treated as a controlled system. All that remained was to detonate the device and confirm the model. The detonation itself lasted only seconds. What followed did not. In the control rooms, the instruments reacted immediately. Seismic sensors lit up. Not as predicted. Not as clean. The explosion traveled through the island faster than expected, along paths the models had marked as stable. The ground did not absorb the energy evenly. It redirected it. Within moments, water deep underground began to move. Pressure surged upward, forcing groundwater toward the surface. In some places, it rose to within a few meters of breaking through. This was not supposed to happen. The models assumed the rock layers would collapse inward, sealing the cavity. Instead, the shock interacted with existing faults, ancient fractures, invisible on the surface, but very real below. Seismic data showed something else. The island itself had shifted. Not dramatically, but measurably. The readings resembled a natural earthquake, not a contained test. The magnitude was unexpected. The pattern was unfamiliar. Engineers began comparing timelines. Depth, yield, rock response. Nothing matched cleanly. What concerned them most was not what had already happened. It was what might still follow. If fractures had opened paths upward, then containment was no longer guaranteed by depth alone. If groundwater could be displaced this easily, then it could also move again. Slower, silently, out of sight. At this stage, there was no visible damage, no crater, no collapse. From above, the island looked unchanged, but below the surface, the assumptions had shifted. The Earth was no longer behaving like a controlled system. The test had crossed from calculation into uncertainty, and the instruments were the first to notice. The warning did not remain abstract for long. Within days, the island began to change. Not gradually, not subtly. The surface started to sink. Near the test site, the ground collapsed inward, forming a vast depression, nearly 2 kilometers across, more than 10 meters deep. This was not cracking. This was failure. Seismic instruments recorded another event. Not an explosion, not a test, but a collapse large enough to resemble an earthquake on its own. The ground had not sealed the damage. It had given way. Long fractures tore across the island. Some stretched for kilometers. Vertical displacement reached several meters. In places, the land no longer aligned with itself. Water followed the damage. A nearby stream was cut off. As the terrain shifted, its flow redirected into the collapsed zone. Over time, the depression filled. What had once been solid ground became a lake. The explosion was over, but the landscape was still adjusting. Along the coastline, the effects extended outward. Sections of shore rose measurably. The island had flexed under forces it was never meant to absorb. This was no longer a theoretical concern. These changes were visible, measurable, permanent. Of the 3 underground tests at Amchitka, only one left marks like these. Kanakin. The ground had absorbed the blast, but it had not recovered. The models had predicted containment. What they produced instead was a scar, one that did not fade with time, one that reshaped the island itself. The detonation lasted seconds. The consequence did not. After Kanakin, there was no announcement of another test. No new shafts were drilled. No deeper devices were prepared. The escalation stopped, not because of panic, not because of a single catastrophic failure, but because the limits were no longer theoretical. The island had changed shape. The ground had fractured. Water had rerouted itself into the damage. These were not projections. They were facts. For the first time, The consequences were visible enough that they could not be reduced to numbers. Canacin had been intended as proof. Proof that depth could guarantee control. Proof that the Earth could absorb even the largest underground detonation. Instead, it demonstrated something else. That containment was conditional. That geology was not passive. And that prediction had margins. No model could eliminate. Officials did not declare the test a disaster. By technical standards, the explosion had been contained. There was no immediate release of radioactive material into the atmosphere. But success had come with a cost. That could not be ignored. The ground had failed in ways that could not be undone. More testing would not refine the model. It would only increase uncertainty. Amchitka was not suited for another escalation. The site shifted from experimentation to observation, from testing what could be done to monitoring what had already been done. Access was restricted. The island became a place of surveys, sampling, and long-term measurement. The question was no longer how deep a weapon could be buried. It was how long the consequences would persist beneath the surface. Canacin was the last underground nuclear test ever conducted at Amchitka. The decision to stop did not come from fear. It came from evidence. The realization that the Earth had already given its answer. And that pushing further would mean asking a question no one could control the response to. The explosion was over. The testing had stopped. But the story did not end there. Amchitka did not return to being just another remote island. It became a place people watched. Scientists returned, not to detonate anything, but to measure. Samples were taken. Water was monitored. The surrounding ocean became part of the study. The concern was no longer the blast itself, but what might move afterward. If fractures had formed beneath the island, they could also become pathways. Slow ones. Invisible ones. Groundwater. Seepage. Transport over time. These were not dramatic processes. They unfolded quietly, over years and decades, for nearby communities and observers. That uncertainty mattered. Environmental groups raised questions that could not be dismissed easily. Could radioactive materials eventually reach the sea? Could they enter marine ecosystems? Could the damage extend beyond the island itself? There were no immediate answers. Official reports emphasized monitoring, long-term assessment, risk evaluation based on models, and continued sampling. The data did not point to an instant environmental collapse, but it also did not allow for absolute reassurance. That gap between what could be measured and what could not yet be ruled out became the aftermath. Amchitka entered a different phase of existence. Not a test site, not a disaster zone, but a reminder. A place where a single decision had altered the ground permanently, and where the consequences could only be followed, not undone. The island no longer represented what humans could do underground. It represented what had already been done, and what still needed to be watched. Canacin was detonated in seconds. Its effects unfolded over years, and some of them are still being measured. The surface tells part of the story. The crater, the fractures, the altered landscape. But below the ground, the picture is less clear. Scientists can model what happened. They can simulate how shock waves traveled, how rock collapsed, how water moved. But models are not memories. They do not preserve the original state. Once the ground was altered, there was no way to return it to what it had been before. That is the first limit. Another lies in time. Groundwater does not move quickly. It travels slowly, sometimes over decades. If pathways were opened by the test, their consequences would not announce themselves. They would emerge gradually, quietly, possibly long after attention had shifted elsewhere. Monitoring can reduce uncertainty. It cannot erase it. Samples can show what is present now. They cannot guarantee what will never appear. This is why Amchitka remains a site of observation. Not because disaster is assumed, but because certainty is impossible. The island exists in a state between reassurance and doubt, between what has been measured and what cannot yet be ruled out. Kanakin was meant to answer a question: how large an explosion could be buried safely underground? Instead, it revealed a different one. How much change can be introduced into the Earth before prediction stops being reliable? That question does not belong to Amchitka alone. It applies wherever humans drill deeper, detonate larger forces, and treat the planet as a system that will always respond on command. The test is over, but the question it raised has no final measurement and no clear end.